It's my pleasure to introduce our session and our next speaker. Our next speaker is Professor Jay Yang, who is department head and professor of computer engineering at Rochester Institute of Technology. I had an interesting conversation last night with Jay about some what I think you'll find some interesting concepts about predictive cyber defense. And let's welcome Jay as he presents his talk, Anticipatory Cyber Defense, Predictive Analytics, Machine Learning, and Simulation.
Thank you. And I also want to thank the organizer for giving me the opportunity to follow Alex's talk. It was a great leading to some what I'm going to talk about. I have some agreement, but disagreement with his comments. I do see that autonomous agents, intelligence, and machines can complement human beings, but there are different kind of intelligence. I do not see the intelligence to be the same, and there should be different types. So I see a lot of values there, and during my presentation, I'm going to show you a few things that hopefully that complements, also learn from the human side of intelligence. So this talk is 3 ongoing projects that's built on culminating experience that we have had in our research group since 2005 when we did a cyber SA project with Air Force. So I'm going to touch upon some of the highlights, but the first thing is to explain this notion. What do I mean by anticipatory cyber defense? So think about this. We human, we are not settling with just detection. We are not just passively detecting and reacting to things that attack us, right? We like to comprehend. We like to anticipate. You, me, everyone here, that we like to do so. So why are we thinking about restricting cyber defense to be only reactive, only detective, right? We shouldn't be thinking about that. So in fact, that many of you are thinking about threat intelligence, other stuff. But I think that we should go even beyond that a little bit. Can we do, instead of weather forecasting, instead of forecasting the trajectory of Hurricane Michael, can we forecast the trajectory of ongoing cyber attacks or attacks that have not even happened? Can we do that? To what limit can we do that? Of course, the end results may not be that great at this point. It is not. I'm going to tell you already that the results are not excellent at this point. But can we develop a science and understanding to what limit can we do that? And can we explore certain type of intelligence algorithms, models, architectures that can make it better? All right? So, of course, there'll be a lot of challenges. I'm going to mention 3 of them that we have been working on. The first challenge is, can we forecast? I'm using the word forecast different from prediction. Forecast, in my terminology, means that I don't have any malicious activities yet. It's not in my network, it's not in my environment, but there might be some anecdotal evidence maybe suggesting something might happen. That's what I mean by forecast. Maybe a week from now, a month from now. That's what I mean by forecasting. So how can we do that? To what limit can we do that? Actually, IARPA has a current program called CASCADES, and we're in part of that program. And I'm going to mention just a little bit about that. I'll focus on the other 2 problems for this talk. The second problem is this. So as Alex pointed out, one of the Ds is very, very small and changing behavior. How do we build models if adversary behavior, malicious activities are changing over time? And so few data is available for us to learn. Even if you can get data, it may change next week. How do you kind of learn in that kind of environment? So if there's no label, we got to recognize and rapidly recognize some of the emerging behaviors, even if it is not perfect. How do we do so? That's the second challenge. The third challenge is that, well, since there's a limited data, since it's evolving, we as humans, we like to simulate. We like to synthesize. We like to be imaginative what might happen. Okay? So we're not restricted by saying that, oh, I only see 5 kind of chairs. I only recognize those 5 kind of chairs. We can imagine what kind of new chairs, different kind of chairs, that can be folded in certain ways. That's still called chairs. So can we use that imaginative simulation as a framework to synthesize scenarios or things that we haven't even seen yet? Third challenge. If you don't believe me that attack behavior is changing over time, I'll show you some data. Most of you may have a lot more data than us. We are in academia, we don't have a lot of open source data that show us how things progress over time in an attack. I'm not talking about single malware. I'm talking about the use of different exploits, scanning techniques over time. These two charts is just a sample data from the collegiate penetration testing competition that's hosted at RIT. We just finished regional this year. We're going to have national in a few weeks. So the competition has 10 student teams penetrating into a network. Last year was the election system. The year before was the healthcare system. This year is about like Uber, represent like a reflecting kind of Uber kind of system. So for 10 teams, and again, this is, many of you know CCDC. CCDC is more defense-oriented, this is more offense-oriented, but ethical offense. Not king of the hill, more like a professional ethical hackers. So these 10 teams that what I'm plotting here are two different teams over time. The x-axis are times. Y-axis are bars showing what kind of exploits, what kind of scanning tools they use over time, and the volume of it, of different types. So different kind of part of the chart, the histogram means different types. You can see already two dimension that see the evolution changing. One is temporally, different attack types, exploits are being used by each team. Also across teams, very different. So we cannot assume there's only 5 models, 10 models, or 50 models. There's going to be continuous evolution of models and behaviors. Okay? So that gives you one element of that. If you have data, you can show more about how attack behavior change over time, there'll be excellent. I think that you should publish that, let the community know more about what does it mean by attack behaviors evolving over time. So knowing that, we've been working on these 3 projects. The first one called Capture, second one ASSERT, and the third one is called CASCADES. Nice acronyms, my student, my colleague came up with it. Capture means that can we capture things very early on from very like open source data that's not really malicious activities? Can we forecast? That was the first challenge we talked about. ASSERT means that we don't, without any labeled ground truths of what kind of attack model, attack behaviors, can we make assertion of the type of attack behavior that's emerging? We may create 50 models. 35 of them are not important. Those are just very common scanning. So we can put it on a low priority, looking at some specific behaviors, how they change things over time, multi-stage attacks. Cascade means that given those limited information, how do we synthesize cascading the type of scenario that might happen? Think about tuning a knob. I want to simulate, I want to see attacker type ABC, state actors BCD. Can I simulate some other kinds of behaviors? They'll be excellent, isn't it? To see what might happen. All right, so first one, capture. So I'm going to have only one slide, very briefly talk about this one. This one, what we have found, what I'm going to focus on just to talk about the challenges. Because this problem of forecasting is so far-reach, right? Can you ever do that? Yeah, you can, but you cannot. The biggest problem there are a lot of problems that includes the data is incomplete. A lot of signal sensors, you say today you got some Twitter feeds that might be indicative someone is going to attack Pentagon. Well, not really. So tomorrow you don't. The signals are incomplete. More importantly is non-stationary. So think about, Alex mentioned about whatever we do, adversary will read about it, right? If we're trying to forecast, trying to link, let's say, Twitter feeds or dark web activities to this kind of attack, you assume that I'm the only one who knows it, whether it's FireEye, Symantec, company, or academia, or government, we're the only one who knows it, you are fooling yourself. Somebody else, oh, so you're linking that, so I'm not going to do that tomorrow. So things are changing so rapidly on the relationship between the signal, the features, to the forecasting attacks. How do you develop this notion of concept period? If you're in machine learning, you might know this notion of concept switch, right? Concept period. So look it up and you can see how that might work out. I think there'll be a lot of tweaks need to be done so they can be very rapidly understanding and say, the model we just developed need to be changed. Okay? In a week, in a few days, in a month, whatever that period is. So those are a few challenges there. I'll be happy to talk more about it, what our progress are, and we have a few papers out, and some other people also have papers out on this side. I'm going to focus a little bit more on the second and the third. The second problem is this. So many of you are working with data. Again, I'm envious of you. You have a lot more data. So in our case, we're limited data, and we want to kind of detect and recognizing, separating the evidence so that we can have this emerging behavior that's popping out, and we're grouping this alert. You can call it about alert correlation without templates, alert correlation without any prior knowledge. And you need to change that along the way. So this is a semi-supervised learning that we kind of integrate both Bayesian, which is supervised, we make it unsupervised, with clustering together. And along the way, we found that one thing that's very, very important, that's not only we want to detect, revise, and change the emerging behavior, we call it empirical models, we also need to accommodate the fact that you could have unseen features. A particular behavior that never exploit that port or that service doesn't mean it will not happen. Right? So how do we accommodate the fact that this unseen could happen in the future? I don't want to miss that. I don't want to misassociate them. So we have done a few things by thinking about the notion of information theory, the entropy to account for that. So we've developed a prototype. I'm going to show you a short video a little bit. So what you're going to see is that as you see the alerts coming in, the model is going to adaptively kind of create it. One line is going to show that the model quality goes down, and then we're going to bring it back up. Quality goes down, bring it back up. It's adaptiveness of the ASSERT. After that, okay, I thought it's 5 minutes. So after that, when we create the model, you're going to see there are multiple models being shown on this visualizer, and we're showing the histogram associated with each model, understanding the type of alerts, the type of signature, the type of exploits, the ports, the services, the temporal, and you can see the graph on the left that shows that within this network, multiple areas of the network showing the same kind of behaviors. And I'm going to speak, oh yeah, okay. So, and then you will see that this actually is coming from the data I just talked about, CPTC, penetration testing competition. 3 teams were shown here. We have total 10 teams, but for this example, I showed only 3 teams. So the 3 teams, you can see that some of the behavior, I'm going to go back just a little bit and pause over there. Pause right here. So you can see that the bottom here, you cannot see very clearly, that's not what I meant, but you see the dots at the bottom. So it's a 1-day competition after lunch break. So before lunch break, all the teams are trying to look at the scanning activities. After that, they start doing their own exploits. You can see that there are more models. The y-axis are the different models being created, generated. So after the lunchtime, there are more models, more behaviors being generated, created, as we expect. The teams were using their morning time, probing, scanning what the network is about, and then in the afternoon, they start doing their different kinds of scanning, different kind of exploits. Still have some scanning, but different kind of exploits. So more models will emerge. Okay? Very interesting observation, which satisfy that what we expect. And our system, our visualizer, allows to explore this a little bit more to forensicness and so on and so forth. So that's a video. Let's just show you that we have this going on, all this math and algorithm behind it. I want to touch upon 2 main findings we have so far. And this is not done. We're going to continue to work on it. Continue to work on improving the features, improving the priors, improving other elements. But 2 findings. So you can see on this chart, there's a blue line, there's a red line. Blue line means that if we don't have this intelligent correlation, intelligent grouping, that grouping without prior models, that we couldn't do very well on predictability. But if we do this intelligent grouping, our predictability over time, the axis is time, enhanced significantly. That's the top chart. The bottom chart, we actually estimate that what is the predictability of unseen features, things that haven't emerged yet. Can we do that? And you'll see that the x-axis is much lower. So here is a 0.75, 0.65, 0.85, and so on and so forth. Here's at a scale of like 0.1, 10%. So of course it's going to be low because predicting unseen is very difficult. Still, blue has been improved to the red. So we'll continue to work on that and kind of see what we can do there. Love to talk to you more about details. The third project that we work on is called CASCADES, or Simulate. This is also an ongoing project. We've done the simulation part of it. We're working on the first half of our system. So the notion here is that can we use limited data, like we just did with ASSERT, capture a little bit characteristic of those attacks, kind of point out, okay, so here are some of the key characteristics and parameters that we can use based on what we extracted, and we know that it's not going to be incomplete. And then we use that to simulate, generate scenario, and analyze their impact to both the network and adversary. That's CASCADES. Again, a very short video. This video shows not the second half of it. When we generate synthetic scenarios on a network, you can see that the network is initially with green, means the boxes are okay, and then one scenario occurs, some boxes become yellow, which is kind of being discovered, and red means they're being exploited. You probably didn't notice on the bottom right, there was a kind of command line window that shows the statistics of maybe around 10,000 scenarios, 1 million scenarios. Think about you use a honeynet, honeybot system, that you may capture a few scenarios. But here you can easily generate a lot of scenarios. Of course, abstraction, not real systems, so they're not replacing the real system. But you can easily generate many, many scenarios to test what if. With that, we have some results, and one of them is published in Alex's book, one of the books by Alex. So the idea here is that I want to test out what if I change my network configuration just a little bit. The top chart over here, the table over here, means is representing a network look like this. Very small network, I know, but it has like 3 layers of 3 zones, 3 layers of firewalls. If we misconfigure one single thing, what happens with 4 kinds of adversary behavior: amateur, expert, comprehensive, and random. By the way, these are not good enough. We need your help to help tell us that what kind of adversary behavior are there. But what this means is that if I change the configuration, how would these 4 different behaviors, does it take more time, cost? Does it take more time for them to succeed in their attack to this target? Does it change their success rate? You can see that for expert, it actually helped them. It's easier for experts to get to the target with that misconfiguration. And same thing for the comprehensive random. Actually, for the amateur, it takes more steps, even with the misconfiguration. This is because the amateurs didn't know what to look at. They randomly, and this is just a kind of anomaly when we run different simulations. So the point is that they give us an capability to simulate what ifs easily. Different adversary behavior, different network configurations. We can even simulate using this concept called real event simulation, important sampling. This is more operation research kind of work. We use that to simulate cases where you can look at this y-axis. It's 10 to the minus 5. So if you have a well-protected network, one very, very specific, this network is modeling after a healthcare network. So a particular patient data is very, very well-protected. It's very little chance that adversary can get in there to the 10 to the minus 5. But even with that case, we can computationally efficiently to simulate what if you modify the connection, what if you add a redundant servers, what if you do something else? How would that change this real event? So that is not an easy fix. We have done that under this, it's a kind of joint things with NISF and NISA. So excellent, we have done something, but we're not done yet, right? This is the notion of anticipatory cyber defense is just beginning. Predictive cyber defense. So how can you augment human analysts? How can you augment the detection with how much can we anticipate? What can we anticipate? And this is definitely not just a computer science, computer engineering, not just a STEM problem. It's also a cross-disciplinary problem. For example, the first problem we talk about, forecasting. They will require a lot of natural language processing, require a lot of this international affairs and policy people to think about giving more indications what is really meaningful to be indicative of a cyber attack, future cyber attack for forecasting. For the second challenge, we have solved some of the problem, but not all of them. For example, we just talked about explainable AI. And I think Alex a very, very good explanation of the DARPA program. It's not really totally explainable. It's to give good indication so that human can trust, can comprehend better on the outcome. Last night I had a conversation with some of my students. They just run some library and give me the results. Say, hey, tell me that why this happened the way. They couldn't do it very well, right? So it's really the interpretation of your result, interpretation of your decision making of those things. I think there's a lot of opportunity there. I want to point it out that deep learning is not the only solution. Deep learning is not the only AI. There are many other ways. Think about we humans really are imaginative, that how do we leveraging that? What kind of intelligence can we build there? This is the last slide. And last but not least, that do not just learn. Let's try to generate new scenarios, explore that, how can we tune? I really want to know more about science of adversary. So how do we tune the knob? What knobs do I need to build to tune? So should I tune that, how to go from an APT or different kind of APT, assisted persistent thread, to something else? How do I tune, what knobs to tune and how to tune them? I think that the community can really explore a lot more there. This is uncharted territory at this point. And a lot of opportunities with partners. So with that, I want to acknowledge my current students, alumni, and some collaborators, and also the funding from IARPAR, National Science Foundation, and past funding organizations that includes NSA, Air Force, Navy, a little bit Army as well. Okay, thank you very much.
Before we get to questions, I just want to point out that if you're unaware, the slides of most talks are available at camlis.org/schedule, or if you click on the speaker name, you'll see PDF slides you can follow along. And also, the timing is important because we are live streaming, and you can find that at camlis.org/stream. So tell your friends, your kids at home can say hello, or whatever. Jay, really excellent talk. I'd like to just begin maybe with a question from the audience, if you don't mind. And that is anybody in the audience aware of any ongoing efforts of this style of anticipatory cyber defense? That's, not maybe outside of the academic community.
Excellent question. I also want to know that.
I was teeing you up for a question, Rich.
The question was whether our approach is doing a top-down, starting with certain kind of models and so on and so forth. Yes and no, right? So yes, we're academia. So, and I don't have expert like you guys in the industry. I only have students and myself and faculty. So the type of model we build on like kill-chain, different kind of attack models that's in the published public domain. So I love to work with some of you if you're interested in some way that see the type of, so for example, ASSERT. ASSERT is a framework as itself. We can accommodate to start a system with some kind of model on the side. We don't need to start with no label whatsoever. We can have some labels, some models. So yes, we definitely want to work with people on that, yes.
Basically, my question is, okay, in that first situation where you have capture, you're looking at a lot of unstructured data, things like Twitter, GDEL, and you're trying to anticipate when and where an attack might occur. And then the second one, you're trying to say, detecting attacks. How do you correlate between when you think an attack is going to occur, where it's going to occur, and then actually when you detect it?
Very good question. First of all, I want to clarify that the two projects are not linked yet. Okay. And we are not experts of natural language processing or international affairs or things of that. So those are collaborations, to clarify that. But the linkage between the two projects in my mind is the following. So if forecast capture can tell us that there's going to be a denial of service attack in your organization, so I'm going to start looking at evidence more from that in the ASSERT side, right? What kind of emerging evidence I should focus on to see that? Maybe put more emphasis on that instead of other emphasis, because it's always about a lot of data. I forgot to repeat the question, but the question was about how to link between capture and assert. Right? So that's the way that we see it. But capture is not done, assert is not done, but that's the way we see how you linked.
Hi, because you come from academia, I have a little open-ended and probably sort of a dumb question, but because you work in anticipatory intelligence also, one of the things that I'm thinking right now is like, what if we assume this to be a game theory problem, and can we sort of say that, okay, how it will converge to a Nash equilibrium, and can we anticipate like next wave of or next different kind of attack instead of like where attack is happening, but what kind of, like, for example, now it's the right time for a ransomware to come into picture, probably in 6 months or 8 months, like that. Thank you.
So I don't think I need to repeat the question. There is a group of people in the community, whether academia, industry, or government, working on game theoretical approach to deal with this kind of problem. The difference, though, is that in the game theoretical approach community, in a very general sense, I do not claim that I know every single work, okay? But in that community, it's looking at, I know the action set of adversary, I know the defense set of defense actions from the defense side, and how it's gonna play out. That's the objective of the work, right? See how they play out, how they will converge, and what's the optimal situation. In our case, we're not thinking about the type of malicious action is limited, or defense action is limited. So there's a slightly different kind of angle there. Personally, you may not agree with me, which is great. Academia is all about debate, right? I do think there's quite some limitations using that to tackle my problem, but it's good to tackle the problem they are tackling.
My question is about sort of instrumentation, and I think it's for the ASSERT data set. How are you sort of collecting and normalizing that data? And is it all network data? Are there endpoint alerts? Sort of talk a little bit about the collection.
So excellent. So we have done other kind of data in the past. In open source data, there's an impact site that actually have those data. UC San Diego, Santa Barbara site, they also have some dark web data, and that we used before. So those data are not good enough for us in the sense of we want to have a little bit knowledge so that we can analyze the result, a little bit knowledge about what actually, how the attack happens, so we can analyze whether we're doing right. So for that, we have used a collegiate penetration testing competition to collect data. And that's different from CCDC, so it's not defense, it's offense. And the data we use from last year is limited in some way. And now we are collecting new data that will have both the network traffic and the endpoint.
We have time for another question.
Okay, great. So I think one thing I was looking for in the talk was a specific example. So I guess this is a question I always have in my mind, that and anything ML-based, what is it doing on top of a rule-based system? Like in a rule-based system where human operators code in all the intelligence, right, based on patterns we've seen in the past. So in terms of ASSERT and like the first two categories, could you talk about like a specific example where a attack was anticipated which was not detected by a human operator?
Great question. I think you're talking about what do I have an example. So just before I came, I actually talked to students, and so I gave you an example. I don't know exact signature, what they look like. We're talking about Suricata alerts. We're using Suricata alerts. And there were a few very unique outlier models that we generated. So we generate two models. They were not grouped together because the system treat them as two different signatures, very unique things. But when human analysts look at them, they say, these two are very similar to each other. The nature of them, the purpose of them are very similar to each other. And those things should be complemented by rule-based kind of models. And those are the things that right now in academia, we couldn't scale it. So for example, if I work with Symantec, FireEye, if we have those rules as a way to kind of lump things together, I think that the system will be a lot more robust. So I do not see this replacing rule-based. I think this and rule-based are complementary of each other.
Thank you, Jay. Let's thank our speaker one more time.